Hello and welcome to the Dustin and Eric Podcast Show, brought to you by Mimosa Networks. Hi, I'm Dustin.
I'm Eric.
Today we're on episode number 24, Link Budgets. What are they and why are they important to the work I'm trying to do? Like, seriously, I already spent enough money on wireless equipment. Why do I have to budget any more money for designing a link too? I don't think that's what link budgets are.
No.
No.
We're talking about RF, connecting. What's it take as far as signal and to get to link 2 points of a long distance radio link
without them failing.
Yeah,
so we're not talking about money today.
Right.
No, but you are talking about budgets.
We are, but not money budgets.
Well, very similar idea, though.
Oh, okay. Well, you'll be able to explain that in a moment. So
RF
our special
budgets.
guest today, who's already chiming in, Vardin Amiri, and he is the king of Mimosa.
Wow.
So
Congratulations.
thanks for being on the show today, King of Mimosa.
Thank you for having me.
Vardin, so tell us a little bit about what you do for those who don't know who you are already.
So I'm a senior sales engineer here with Mimosa. I basically help and support the sales organization from a technical perspective. So I help them with link budgets is one of the things I help them out with.
And so I thought you'd be a perfect addition to the show today. And again, I appreciate you being here.
I like the word perfect.
Perfect. King of Mimosa. All right, so let's go ahead
El Rey de
and
Mimosa.
so let's go ahead and move into our main course today, which is link budgets. So this is how you make a mimosa. Oh, wait, how did this get in here?
That's funny.
Wouldn't that be the main course?
This is the main course, mimosas.
All right.
A 1/4 cup orange juice and 3/4 cup champagne chilled.
Extra pulp on that juice?
Extra pulp. Okay, so that's totally not part of the show. So anyway, link budget.
Wait, everyone in Silicon Valley runs on alcohol?
Yes. Who here in this building does not drink alcohol?
Unless you run on batteries.
Except King Vardin, who only drinks Bud Light Lime. So, all right. So, link budget is the sum of power gains and losses between a transmitter and a receiver. The receiver must have adequate signal strength to properly interpret the message. So, for those that are watching from home, we've got a cool little graph here, or little graphic here that shows you all that's taken into account of link budget. But the link budget takes in transmit power, which is dBm, cable loss in dB, transmit or TX antenna gain from the antenna you have attached or the integrated antenna, dBi, free space path loss, which is the loss between point A and point B. Of course, that increases as distance increases.
Or as frequency increases, we see losses increase.
Right. Mm-hmm. You have atmospheric loss. You have rain fade, ambient loss, RX antenna gain, RX cable loss, and this all culminates into receive power, dBm.
And for those people who actually make their own cables and they're not so great at making cables, you may want to put connector loss in there as well.
Sure.
That's right.
And adapters and things like that. Adapters and RF connectors at the end of the lines can contribute to, say, depend on the frequency, maybe 1/3 of a dB, maybe a half.
Sure.
And
But you always have the option to buy pre-connectorized cables as well. I believe Mimosa ships those with their antennas, don't they?
We do. We have some really awesome LMR 240 cables that go with the N545 X2s, X4s, and the N5360.
with built-in little rubber boots.
Perfect.
For weather.
And they slide right on and perfectly weatherproof your cable. But of course, you can do your own weatherproofing as well. It's completely up to you.
Yep. And for on the slide here, we see pluses and minuses. So we have pluses like how much transmit power. So that's bonus energy. That's energy. That's a plus number. And antenna gain. We've got a plus there. We can add that as a gain, and such. And the receiver gain as well. And then there's minuses, so you'll come up to some you'll have values there, a sum of things, and then we're going to have insertion losses and other things that we can subtract from that positive number.
So we're doing a lot of adding and subtracting.
Yeah,
from this
just
number.
simple pluses and some minuses in this case.
Right. So one of the big factors is the thermal noise floor. So that is the sum of noise sources in the environment. So this takes into account thermal noise, cosmic, and atmospheric. The effects of noise on radio transmission depends on temperature, bandwidth, and antenna directionality. So, Vardin, why don't you tell me a little bit about noise floor and why that's so important to the link budget?
Well, you want to have a very low noise floor. So the lower the noise floor, the higher the signal to noise ratio. So basically, you want your radiated signal to be a lot stronger than the actual noise floor. So basically, the better SNR, so the signal to noise, will give you basically a higher SNR, thus giving you higher modulation. Thus, if you have a higher modulation, it means you can pass more traffic over the link.
Okay, since you're talking about SNR, Eric, do you have any good examples on how to describe SNR in a different setup or scenario than just RF?
I was going to go on your line there, and it's a
You
sum.
notice how I'm louder than Eric? That's a better SNR.
Oh, okay.
That's a better signal.
And then actually, when we're not speaking, there's the noise floor.
Right. So
And then so here's the floor. It's quiet except for a little fan there. And here's usable information up here. So this is up here. The difference from the lowest signal, the usable, the positive signal, and that average floor, the sum is the ratio or the difference, the signal noise ratio. That's the difference.
And for those of you who can't see Eric doing all of his hand gestures and the picture that we have here of two diners in a restaurant with the headphones on.
You mentioned Mimosa before, right? And talked about alcohol, and that's all relating to bars. So a lot of you go to bars and have a drink.
Yeah.
You notice when there's a lot of people
Right.
chatting and talking, and you want to talk to the friend that sits right next to you, and you got to speak louder.
Yeah.
Well, just assume everybody else is a noise.
Yeah.
So therefore, you raise your volume to basically get a better signal to noise, and the noise is the rest of the crowd in the bar.
And that noise, even with your buddies sitting to the left and right of you, they're almost at the same noise floor, so there is almost no separation. So it's very difficult to understand or get intelligible, useful information. So they were yelling and we're competing with the floor there.
you know how people cup their hands over their ears?
Yeah.
You're basically increasing your receiver
go.
signal strength. You're upping your antenna gain, basically,
Hey, is that
so you can hear
beamforming?
better.
Is that beamforming?
Audionic
Maybe.
beamforming.
Yeah.
ABF.
Or you do two hands, one on each ear,
Oh.
to doubly increase
Wow,
your antenna
3
gain.
dB.
So it definitely increases what you can hear. You can hear your friends better in the bar.
That's
or
what we want.
across
We
the
want to
room.
squeeze
So-
every bit of information and separate that information from the floor. Yeah.
So since we're talking about SNR, there are things that actually causes your modulation rates to drop or to increase as well. So of course you want to aim for the highest modulation rate to best combat, signal to noise ratios. So you want to try and up your gain. But there's things here that decrease that. So low power and low gain. So long distance, so free space path loss. Obstructions on the link. You also have fade sources like rain or snow. You also have other nearby radios that can cause fade. And then the biggest and hardest one to combat, which is ducting, which is temperature inversions over valleys or over water, which we have a 56-mile link that we've talked about a lot in the past that is mainly over water. So we see a lot of temperature inversions on that link as well.
So we get on the 56-mile link. We've got an envelope of energy on point A and then B, and everything's fine. And then we'll have a thermal, two different temperature. An inversion will have two different temperature layers, and that signal is caught in that thermal layer, and then we see a direct shot on the link, and we'll also see some phase issues. We'll see some of that energy bounce or reflect within that thermal duct from point A to B, and so there's some phasing things. Sometimes that helps propagates the signal a little better, and other times it certainly attenuates it. So there's all kinds of things, and we'll see the performance often suffer for that.
Right. So earlier we mentioned atmospheric losses. So water vapor and oxygen in the atmosphere become excited at their resonant frequencies and absorb energy. So once you get above 5 gigahertz, the effect becomes increasingly significant. Beyond 20 gigahertz, the effect is severe. So which is it? Is it 70 or 80 that resonates on the same frequency as oxygen? Is it absorbed by it?
72-ish or 3? Is that
No,
somewhere in
it's
there?
about 60.
Where's it at?
Oh, is it
about
60?
60? Yeah.
Okay.
There's a water
Yeah.
table. This affects those upper millimeter waves, and also, and if you get into fiber optics or optical transmissions, we'll see the water table come in there too. There's some hot spots that just attack signal.
So that's why
it's
when
all related.
when your signal or when your frequency goes higher up, the shorter the distance you can make your link, unless you have a huge like antenna, or you increase your gain or your transmit power by a lot, but you still shrink your distance as you go up higher in frequency because of oxygen or water absorption.
Yeah, the wavelength gets smaller, so we see these wavelengths get shrink and get really pinpoint. But there's things that happen up there, and that's like this. It approaches these water areas and tables, and we see different atmospherics attacking or attenuating these signals that we need. And as you go down lower in frequency, you don't see as much as this type of stuff.
Right. So one more thing we'll talk about here is the bandwidth effect. So in theory, as SNR or channel width increases, data capacity increases, but you also get increased noise floor and a potential to encounter more interference across that channel. So these two items will definitely cause lower SNRs, and smaller channel widths will increase the SNR values for you, so you have a larger gap between your signal and your noise floors. So if you have problems with low signal levels, or you're having problems with your SNR,
maybe tighten the bandwidth up a little.
right, you would shrink your channel width to help increase that. So here's an example using the Mimosa design tool, which we go in and automatically calculate the link budget for you. So if you're looking at this from home, we have a 2x80 setup here in the design tool, and it calculates everything. You can see that your SNR value is only at 48 dB for this particular link. The only thing we change on the next slide is we change that from a 2x80 to a 1x20, and you can see how your SNR increases to 57 dB on that link. So you can see just how severely using 20 megahertz over 160 megahertz of spectrum can increase the noise floor or decrease the noise floor for you.
And obviously you kept all the other parameters the same.
Right. Everything else is exactly the same.
We just changed the channel width.
Right.
Yeah.
So Vardin, if we were to design a link budget, what margins are we looking for? Like, what's the goal?
So the goal is basically, as the whole purpose of this podcast is basically budget. So the goal is, what are you trying to achieve? So there's distance, there's TX power, there's a lot of variables there that need to be adjusted, and we here in the United States need to abide by the FCC rules. So based on the FCC rules, based on basically the amount of capacity we need, the antenna gains and all that, we go through the pluses and minuses you discussed, or through the Mimosa network design tool, and we can come to a link budget that is provided. And the SNR that is given, it basically reflects the modulation that you can operate in. So typically, if you want to operate at 256 QAM56, which is the highest order modulation, you need to ensure an SNR greater than 28. So if you get more than 28, you should be able to operate at the highest order modulation. Now, if your link budget calculation, demonstrates somehow, or for whatever reason, like 20 dB SNR, therefore you will drop in terms of modulation. You got to be careful is that as the SNR drops closer and closer to 5 or below 5 means basically you're losing link. Now, keep one thing in mind, that all this is based on the receive sensitivity of the radio. So having said all that, you want to ensure if you need 28 dB to operate in 256 QAM56, you need to add a little bit more margin to that for the reason of you get pointing errors, you may get some kind of additional loss in the cables and all that. So once you take all that into consideration, you may want to calculate 5 to 10 dB additional margin.
And where can we get that? Maybe antenna gain, increase antenna size?
You can increase antenna size if you have room for TX power. Every area that Dustin demonstrated before on the plus and minuses, the first, I think, 3 or 4 slides, you want to try to increase the pluses and minimize the minuses.
Right. So Vardin, should I or customers design their links with the best possible link or the worst possible link, then so they can better prepare for their deployment?
Well, especially in an unlicensed band, you always want to basically over-design your link because you really don't know what's out there until you go out there in terms of noise. So you want to basically
spectrum analysis, or if you can look at,
or you can just basically start off if you know that let's say 15 dBi or 16 dBi antenna would be sufficient. Go ahead with a 25 dBi. This gives you an additional 10 dBi on each end of the link in terms of margin.
Right.
you're putting some a little bit of padding in there. Yeah.
Yep.
In the design.
Always better to be safe than sorry.
Yeah.
So, is there anything else that either of you two want to add to this before we finish up? Is there anything that we missed that you want to, add additional, or anything else you want to cover?
We have white papers. We have some video podcast on it. It's on the help, on the backhaul help sections, and just the same stuff. And then come into chat. We talk budget and optimal link performance daily.
Yeah, come in the chat. We'll give you Vardin's personal address, phone number, personal email, any way to contact him on the weekends. So you can ask him questions.
No worries, I'm always traveling to customer sites.
Yeah, some of you guys that watch this, you might actually recognize Vardin and I. We've both gone to customer sites together a lot, and Vardin does a lot more travel than I do. So you never know, you might see him sooner or later. So
Frequent flyer.
But anyway, all right, guys. Well, I guess that's it for episode 24. Catch us next time on episode 25.
Thanks, Vardin.
Thank you very much, guys. Thanks for having me.
Thanks for watching.
All right.
Thanks for tuning in. Please hit the subscribe or follow button to stay up to date with our latest podcast, which will be available on YouTube, iTunes, Google Play, and SoundCloud.